Here's a video I want to do to introduce exponential functions and compare them to linear functions. And so what we have here is two examples of population growth. So one, both of them are a city with 10,000 people. The first one, they're increasing, the first year it increases by 500 people in both cases. But the difference is on the left, it's increasing by 500 people per year. Every year, 500 people, 500 people, 500 people, okay? So the population will be 10,000, then 10,500, then 11,000, then 11,500. And we can get a nice formula for that. That just means we start at 10,000, and every year we add 500 times t. That's a nice slope. People per year is constant. So there's a nice, every year you add 500 people and you get a nice linear function, okay? What about in the other case though? Here we're talking about it increases by 5% per year. So the difference in a linear, you're increasing by an absolute value each amount, 500 people per year. In an exponential, you're increasing by a percent, a relative change each year. So we're increasing by 5% each year. And we've talked about this a little bit. Here's the formula. You'd again start at 10,000. And to increase by 5%, we've talked about the key is you have a growth factor of 1.05. 100% plus 5% is 105%, 1.05. And so after that first year, in this case, you match the linear case, you've also increased by 500 people. The difference is the second year, when you multiply again by 1.05, you get the initial amount times 1.05 squared. Now you've got 25 extra people here, 11,025 compared to just 11,000 in the linear case, because those extra 500 people, they increased by 5% too. And 5% of that extra 500 the first year is 25. So that you get increases on the increases. And so each year exponential growth grows a little faster. The third year, like we've said before, you would multiply that thing again by 1.05. And so if you're multiplying by some growth factor every so often, every year, you're eventually going to have an exponent, that growth factor to an exponent. And so what happens to the graphs of those? Well, if you graph the population over the 5 years, the linear one will go up by 500 each time, and it's just up 500. But the exponential one goes up 5% each time. And so that is a bigger amount each time, and it'll expand and increase faster and faster. That's exponential growth. What about the reverse situation? In this case, let's say you have a car and it's depreciating, it's losing value every year. It could either lose value linearly, or it could lose value exponentially as a percent each year. And so in the linear case, on the left, let's say it decreases by $2,000 per year. Then again, we can get a nice formula. It's a 20,000 to start, then 18,000, then 16,000, and it's 2,000 or 20,000 minus 2,000 times the number of years, and that's dollars per year. So that's a nice linear change. Every year you decrease by $2,000. What's the difference in an exponential function? In an exponential function, every year you decrease by 10%. And so that growth factor, in this case is a decreasing factor, a decay factor, is 1 minus 10%, which is just 90%. So each year the value is 90% of the previous year's value as it decreases. And so after 2 years, it's 90% squared, 0.9 squared, and that comes out to 16,200. So in this case, you're actually decreasing slower than you are in the linear case, because now that second decrease is 90% of the smaller amount. So the decrease is less. So the car is actually valued more in the second year, 1620 versus, or 16,200 versus 16,000. So what's a formula for that in general? It's going to be the initial amount, 20,000, times 0.90, 90%, to the t years. It's an exponential formula, right? And so what does the graph of that look like? Well, the linear one is the red straight line. And if the car was worth $20,000 and it decreases by $2,000 every year, after 10 years, it's going to have value 0, right? That's what the red line does. The purple curve, though, is the decaying exponential function. And what that is, it starts at 20,000 and it decreases by 90%, or sorry, it decreases by 10% each year. And so after 10 years, it's going to be down here. If it decreases by 10% 10 times, that's 90% of 90% of 90% of 90% 10 times. And that comes down to, if I calculated right, about $7,000. So when it depreciates exponentially, then it'll be a long, slower decline, and it'll never quite hit 0. It'll always be a small, tiny fraction. Even after 20 years, it's still $2,000. And even when after a long time, when it's worth $1, the next year it's worth 90 cents. Then the next year it's worth 81 cents. So that kind of goes, and it never reaches 0. That's one of the things with exponential functions. So let me show you what a formula might look like for this, a general formula. This is what we're going to talk about next week. So what we did with percent increases was the new value is the original value, or I'm going to call it the initial value, times some growth factor, 1 plus a rate. So that could be initial times a growth factor. So this could be like a 10% increase would be 1.10. A 10% decrease would be 1 minus 10%. Doubling every year could be, or every so often could be double. Whatever that growth factor is, double every period. Depends on how they talk about the growth. And so what we're going to do is, so now, what happens here? We've got, if we let it grow for, say, t years or days or hours or whatever the context is, then it's going to, like we did before, we're going to multiply by that growth factor t times. But in a lot of, so we're going to get an exponential function that looks like this. But in a lot of situations, the way they're going to describe the growth factor is it's going to grow, it's going to increase every quarter, so 4 times a year. And so if it's 4 times a year, or whatever p is, the number of growth periods per year, it's going to be t times 4. So let me expand that box to get the full thing. So that would mean up here in an exponent, that's the number of times we multiply by the growth factor. The number of growth periods in t years or days or whatever the units are, okay? So that'll say we have an initial value, and every period, every month or week or day, we multiply by this growth factor, and the exponent is the number of times we multiply. And so we're going to use that formula in lots of contexts to explore exponential functions either growing or decaying as we go.